In the previous video, we looked at the properties that were important for a star, and in particular, the sun. Now what we're going to do is kind of dissect the sun and look at its anatomy and physiology, look at how it's structured underneath, and come to some understanding of how those important properties are related to its internal structure. All right, so first of all, the sun is a big ball of hydrogen plasma. I should say that plasma, if you're not familiar with that, is a gas of charges, a gas of electrical charges. So we've talked about how hot the sun is, how the temperature is so high. Well, what that means is that the gases, which are atoms, normally gases are made of atoms, and those atoms are protons, neutrons with electron clouds. Well, when the temperature gets so high, the electrons are not able to stay attached to the nuclei. And so that's where you get a plasma. You have the nuclei flying around and then the electrons flying around, and they're not together anymore. So you don't have atoms like you would in just a regular gas. You have a charged plasma. Now, the plasma of the sun is not uniform throughout. It has layers, and each of those layers has a different function. So you can see in the picture here all of the layers labeled. If we start from the center, we have the core. Moving out, we end up in the radiative zone, and then into the convection zone, and then into the photosphere, the chromosphere, and the corona. There's some other things labeled on here like prominences and sunspots. We'll talk about those later on. Those are not separate layers. They exist within layers of the sun. But those are the layers going from the inside to the outside. And so you should know the order in which they come in the sun. Now, if we look at temperature and density, they decrease from the center. So if you move, so here's temperature and here's density. If you move from the center, which is this side, outwards, you find that the temperature drops. So it's hottest at the center and it cools to the edge. This would be the same for the Earth. And also with density, it's most dense at the core and it gets less dense as you go out. Neither of these things is particularly surprising. The Earth behaves in the same sort of way. Interestingly, what happens with the temperature in the corona is that in the outer atmosphere of the sun is that it heats back up. So let's look at the scale here. The corona is 10 to the 6 Kelvin, which is 1,000,000 Kelvin. The core is 15 million Kelvin. So the corona is actually almost as hot as the core of the sun and much hotter than the radiative zone and the convection zone. So something interesting happens, and this is a matter of current active research to understand the physics of how the corona heats up the way it is. And I believe the working theory is that it has to do with sound energy. The actual atmosphere of the sun is so loud, and that sound energy is actually causing percussive effects that are heating up the gas in the solar corona. One other thing in here, there's this region called the transition region. I'm just in the previous slide labeling photosphere, chromosphere, corona. Technically, there's another layer in between the corona to the chromosphere. It's really called the transition region because the properties transition from what they are in the chromosphere to what they are in the corona over this thin layer inside the solar atmosphere. All right, so the temperature in these layers is distinguished here. So the photosphere has a different temperature. It sort of decreases and then increases within the photosphere. In the chromosphere, the temperature goes from down here to here, and then there's a from down here to up here, and then in the transition region it ramps up dramatically to what it is in the corona. Now, what's causing the temperature of the sun and what is balancing the gravity pressure to create hydrostatic equilibrium is a process called nuclear fusion. And so if we look at this diagram here on the left, there are two different processes. There's this process, and then there's this one. Now this one, you have two different nuclei coming together to create a bigger nuclei. This is fusion. This is when two nuclei are combined together into one. The inverse of that would be taking a big nuclei and splitting it up into smaller ones, and this is called fission. So we have fusion here and fission here. Both of these processes can create energy. So on Earth, we produce energy using nuclear fission. So our nuclear plants work on fission. In the sun, it produces energy using fusion. And both of these processes have a tremendous amount of energy. For fusion, you can fuse elements that are smaller than iron, and for fission, you can split elements that are bigger than iron. So you can't fission hydrogen or you can't fission helium, but you can fusion them. And the sun is made of hydrogen, and so it works on the process of fusion. It squeezes them together. The gravity squeezes them together until fusion happens. Fusion releases energy, and that reaction, the pressure from that reaction, is what pushes back against gravity, and ultimately the sun finds its equilibrium. Now specifically, the process that the sun goes through is called the proton-proton chain. And it's called that because a hydrogen nucleus is just a single proton. So the core of the sun is a plasma of protons and electrons. But the protons, so here they're labeled in blue, will collide together with such pressure that they fuse together, and that fusion process creates a chain reaction. So two hydrogens fuse together, creating this thing, which is called deuterium. You don't need to memorize all of these different things, but what's important to know is the beginning and the end. So I'll go through this sort of quickly. You have hydrogens coming together to create deuterium, and in that process, a positive charge gets released and a thing called a neutrino gets released. We're not going to talk much about these things here. They're not material to what we need to know, but they are created in the reaction. Then these deuterium will collide with other hydrogens, creating helium-3, and then helium-3s will collide together, creating a stable helium nucleus, so helium-4, which is 2 protons, 2 neutrons. And then 2 of the hydrogen, the protons, will be released as well. But in this stage of the reaction, the fusion here, a gamma ray gets released, and that gamma ray is the energy that's produced, or the bulk of the energy, the light energy that gets produced is that gamma ray. Okay, so the way we can think of this in summary is that protons or hydrogen nuclei go in, and helium nuclei and gamma rays come out. So you've gone from something that's made up of single protons to something that is a bigger nucleus, so you've created fusion, and also energy comes out in that process. So the energy generation is happening in the core, and that's what defines the core. Everywhere inside the core, nuclear fusion is happening. Once you get outside of the range where nuclear fusion is happening, you have the radiation zone. So there, fusion isn't happening, but the light, the gamma rays, are radiating through. But the material of the sun is still very, very dense there, and so it can't just get out of the sun in a straight shot. So what this picture is illustrating is the sort of ping-ponging action of the gamma rays as it's leaving the core. So if this is the core down here, it will eventually hit a hydrogen and then hit another hydrogen and hit another hydrogen, and it will keep bouncing around there. Now this random sequence of collisions is called the random walk, and the radiative zone is where the random walk happens. Now light moves extremely fast, but the material of the sun is so dense that it takes 100,000 years for that gamma ray to make it from one side of the radiation zone to the other. And during that time, every collision that it makes with a hydrogen atom, it's losing a little bit of energy. So the gamma ray hits this proton. Well, that collision means that the proton gets some of its energy. And what happens when a photon loses energy? Well, it means its wavelength gets a little bit longer. So by the time these gamma rays get through the radiation zone, or radiative zone, I go back and forth with that because some books call it the radiation zone and some call it the radiative zone. There's really no difference. They mean the same thing. But by the time these photons go through this zone, they end up as ultraviolet. So they're almost visible light photons when they make their way through. All right, now we've got beyond that radiative zone, the material of the sun is not quite as dense anymore. It can flow a little bit more freely. Now, the top of the radiative zone, or the bottom of the convection zone, is really hot still. But the top of the convection zone, by the time you get to the top, it's cooled down quite a bit. So you have a big temperature gradient in the plasma. And what that causes is a circulation of the plasma. So you probably are familiar with the idea that hot air cools and cool air sinks. Well, hot plasma rises and cool plasma sinks. And that process is called convection. And so in this layer of the sun, you have a lot of convection of the plasma. And at the top of that convection zone, the surface of the sun is boiling. It's a boiling plasma. The hot is coming up and bubbling, and the cool is sinking back down. So at the top of that convection zone, you're meeting the actual visible surface of the sun, which we call the photosphere. This is where the light leaves the sun to get to us. So when you look outside and you see all this light around, that light has made its way from the core of the sun through the radiative zone for 100,000 years, through the convection zone, and then to the photosphere, and then it was released. Now that base layer underneath of the convection zone, where it's boiling, means that the surface looks really granulated. We call this granulation, that what we're seeing in this picture, granulation. So this is granulation in the photosphere. And you'll also, so this is sort of light dark regions. This is the bubbles of the boiling. But then within that, you might also see bigger dark spots that are called sunspots. I'll note that the dark and light are differences in temperature. So where it's brighter, it's hotter, and where it's darker, it's cooler. But that by no means it's cold or anything. It's just not quite as bright. So this dark spot is not really dark in the sense that you would think of it. It's actually extremely bright. It's just not nearly as bright as the plasma around it. And then last point on this is that the temperature of the star, which I've said is the surface temperature, is the temperature of the photosphere. So when I said the surface temperature of the sun is 5,778 Kelvin, that's the temperature of this photosphere layer. All right, so now we have another diagram showing these layers, photosphere, then chromosphere, and outside of the photosphere, what we're calling this region is now the atmosphere of the sun. So the light that we're getting is from the photosphere. Everything above that we call the solar atmosphere. And that includes the chromosphere and the solar corona. The visible light easily passes through those regions, and so when we get it, it hasn't really been affected by those layers. But the atmosphere is interesting in its own right, and that'll be a lot of what we talk about in the video on the solar activity. So there's a lot of real interesting things happening in the outer atmosphere of the sun. Now, the only time we can see the corona is when we block out the light from the sun. So you either have to physically block it out, like in this image here, the astronomers pointed a telescope at the sun with a disk to block the photosphere. And then when you do that, you can see the corona around the outside. The other time we can see this is during a solar eclipse, when the moon passes in front and blocks the light from the photosphere. Then you can see the solar corona. Outside of that, this is sort of never visible to us. When you're looking up at the sun and you think you see sun rays, that's really scattered light around the sun. It's not the solar corona. You'd only really see the solar corona when you can block out the light from the photosphere.